Okay, so welcome to this set of lectures about imaging and deconvolution. This morning we will speak mostly about single field imaging. Okay, so I will first explain you why imaging and deconvolve is useful in the first place, and then I will speak about technical details about imaging and deconvolutions. So okay, let's assume that you had a proposal that is accepted, that has been observed at NOEMA, and you're invited here to spend 1 week to make to reduce it, and you end up with visibilities that have been calibrated. So this is one example where I'm showing the amplitude as a function of the UV distance and the phase as a function of UV distance for one channel of this data set, approximately 220,000 visibilities. And so the $1 million questions for you is, what is this object? Any idea? What kind of object is it? Is it a point source? Is it a galaxy? Is it a protoplanetary disk? Any idea? No? Well, that's normal that you have difficulties to find what it is. It's because our mind is not made to sink into the Fourier plane. And that's why it's much easier to go to the image plane. This is exactly the same. This is exactly the same image, except that here you recognize immediately that this is a galaxy. In fact, this is the 12C0120 emission of M51 at 1 arc-second. This is the IRAMK program pose. And it's easy to do some science on this image while doing some science on this data set is not obvious. That's why we want to image the data. Okay, so we have a set of calibrated visibility in the UV plane. So to first order, we will consider that the UV plane is the Fourier plane. So there are two possibilities. Either I've just told you that doing some science in the image plane, it's easier. Unfortunately, there are some mathematical transforms that are needed to go from the UV planes to the image plane. And those transforms come with some artifacts. Okay, and so the goal of these lectures will be to try to understand those artifacts. And so there is a second possibility, and there will be a dedicated lecture by Sebastian Müller to try to do the analysis directly in the UV plane. So because in the UV plane, we will avoid all the artifacts of going into the image plane, it's always better, but in fact, it's not very often possible. It's possible only for simple sources like point sources or disk. So the goal of these lectures will be to understand the effect of the imaging process on the resolution, the field of view, the reliability of the image, the noise level, and its spatial repartition. Okay, as the UV plane is related to the Fourier plane, I'm starting by making a few reminders about the mathematical properties of the Fourier transform. The first important properties that we will use several times is the fact that the Fourier transform of the product of two functions is a convolution of the Fourier transform of the functions. Let's do it again. So if you have the function f1 and its Fourier transform f1 tilde, and a function f2 and its Fourier transform f2 tilde, you're taking the product of f1 and f2, you're making the Fourier transform of this product, and you end up with the convolution of the Fourier transform of f1 by the Fourier transform of f2, okay? And this is a property that we will use several times. The second set of properties that are important when you're dealing with Fourier transform is that the smallest UV distance in the UV plane will be related to the image size in the image plane, okay? And the reverse is true also. The largest UV distance that I'm calling here bandwidth size in the UV plane is related to the pixel size in the image plane. A related property is that if you have a function that has a finite support in the UV plane, then it means that it will have an infinite support in the image plane, and the reverse is true also. And finally, the last important property that we will use in this lecture is the fact that the Fourier transform evaluated at the zero spatial frequency in the UV plane is equal to the integral of the function in the image plane. So let's assume that you have an image in the image plane. You're computing the flux in this image, so you're summing the intensities. Then, by Fourier transform, the total flux in your image will be exactly the value of the visibility function at the center of your UV plane. Okay? Okay. So yesterday, Frédéric showed you that the measurement equation of an interferometer is this one. The visibility sample for a baseline BEG is equal to the 2D Fourier transform of the product of the primary beam times the intensity of the source sample in BEG plus some noise. So what is the impact of this measurement equation on your data? First, we are not observing directly the source of the intensity of the source. We are observing the product of the primary beam of your 15-meter antennas times the source of the intensity. This means that the primary beams distort your information on sky. The second thing that happens is that you have noise. So at some point, if you're searching for faint signals, you have sensitivity issues. And the third thing is that you have an irregular limited sampling. So here I'm showing the sampling in the UV plane. So each cross is one measurement of the visibility, so in blue and green. So the first thing you see is that you have an ellipse. You have no information outside the large red ellipse. This is just due to the fact that you have a limited angular resolution in the image plane, which is related to the largest distance measured in the UV plane. Okay? So limited high spatial frequency mean limited resolutions. Another thing that is less obvious is the fact that inside you have a red inner circle here, and inside this circle you have no measurement at all. So we will see this, so no low spatial frequency measurements. We will see that this makes some problems when we are doing wide field imaging. And now, if we're looking in between the two ellipses, we see that we don't have full sampling of the UV planes. You see, for instance, that those regions are completely devoid of measurement. So the mean cruise criterion is not respected. And so all those cause of problems will imply that you have lost information. Okay? You don't have a complete information on your source. Let's try to understand now what is the impact of the irregular limited sampling on the image in the image plane. So again, the measurement equation, and let's make a few definitions first. So let's define the visibility function, that is the 2D Fourier transform of the product of B primary times the source intensity. This is a continuous function, but we're sampling it at some particular position in the UV plane. And so we are introducing the sampling function. Sampling function to first order is defined as SUV equal 1 for UV points where the visibility are measured, and 0 everywhere else. And we will just define what we call the dirty beam as the inverse to the Fourier transform of the sampling function. Why not? Okay. So now what we want to do is go from the UV plane to the image plane. In order to do this, we will make a 2D Fourier transform, inverse Fourier transform of the visibility of the measurement equation. Okay. So let's forget for now the fact that we have noise, and let's assume that we will make we can rewrite VEG as the product of the visibility, continuous visibility functions times the sampling function. Okay. And we are taking the inverse to the Fourier transform of this product, S times V. And we call this the dirty image. So we are using the first Fourier transform property. We have a product of functions. So by doing the Fourier transform, we obtain the convolution of the inverse to the Fourier transform of the sampling function and the inverse to the Fourier transform of V. The inverse to the Fourier transform of V is directly B primes times I source. This is this definition here. And the inverse to the Fourier transform of S is B dirty. So you end up with the fact that the dirty image is equal to the dirty beams convolved by the primary beam times the intensity of the source. Let's try to understand what is the convolution by the dirty beam. What does it mean, convolving by the dirty beam? And in order to do this, we will try to compute the point spread function of the instrument. The point spread function is the response of the instrument, of the interferometer, to a point source. Okay, let's take a point source of intensity E total that is located as a fast center in your at the direction you're observing with the antenna. So because this is the direction you're observing, so first, because E total is a constant, you can extract it from the convolution and put it in front of this convolution. And you end up, so a point source in mathematics is described as the Dirac. So you end up by E total times B dirty convolved by a Dirac. But a Dirac, the convolution of the function by a Dirac is this function. Okay? So you end up that if you're taking at input a point source of intensity E total, you end up as the response E dirty, the dirty image, equal E total times B dirty. So you can rewrite it by B dirty is equals to the normalized dirty image by the intensity of the point source. And thus, the response of the normalized response of your interferometer to a point source is equally B dirty. Said otherwise, B dirty is the point spread function of your interferometer. Okay? Why do we need to deconvolve? So I've just explained you that the dirty image is the convolution in the image plane of B dirty by the product of the source intensity and the primary beam. So let's forget for a moment the fact that we have the primary beam here. Let's assume that the sky intensity of your source, this is a protoplanetary disk, and you have a ring. And let's assume that your dirty beam is this, the point spread function of your instrument is this function. This is the dirty beam. So what you will measure, the dirty image, is the convolution of this one by this one. This is shown here. This is the dirty image. So you see that that's what you get when you're going from the UV planes to the image plane. So you've been measuring with NOEMA this source, and what you get is the dirty image here. So you see that on this dirty image, it's difficult to recognize that your source is a ring. Okay, you have more the impression that this is a disk, and this is due to the convolution. Okay, so it's difficult to do science on the dirty image. And fortunately, there exists a class of algorithms that is called deconvolution whose goal is to deliver a clean image that is compatible with the sky intensity distributions. And here I'm doing the deconvolution of this image, and I obtain this image. So we see, now we recognize that we have a ring, so it's much closer to the source model. It's not exactly the source model because there are some limits. First, you have a given limited resolution, and second, you have noise. Okay? So deconvolution, the goal of deconvolution is to make an image that is much closer and compatible to the sky through intensity. Okay, so you have calibrated visibilities. We will do Fourier transform to obtain a dirty beam and a dirty image. Then we will deconvolve to make a clean beam and a clean image. Then you can visualize it, make some analysis in your image plane in order to get some physical information on your source. Once you have the physical information on your source, maybe you can write a paper, but on this one, I cannot help you. On the other ones, mappings will help you to do plenty of things. Okay, so let's first start with the Fourier transform. So there are two kinds of Fourier transforms. The direct Fourier transforms, the advantage is that it uses directly the regular sampling. The inconvenience is that it is slow. In fact, the Fourier transform has been invented by Joseph Fourier, probably in Grenoble, I'm not completely sure, in the middle of the 19th century. But in fact, it's not before the middle of the 20th century when the fast Fourier transform that the Fourier transform had plenty of application in science. And why? It's because in the fast Fourier transform, you have a very quick computation of the Fourier transform when the image of the size is the power of 2. The inconvenience of the fast Fourier transform is that you need a regular grid. Okay? You can't use it directly on irregular samplings. So this means that you will need to make an additional step that is called gradings to go from irregular samplings to regular samplings. In practice, the speed factor is so large that everybody is using the fast Fourier transform. The direct Fourier transform is much too slow in order to be used on data. Okay, let's speak about grading. So the idea of grading is that you have your measurements that are the blue and the pink points, which are irregularly sampled on the UV plane. And what you want to do is make a grid of points for which you will have one value per pixel. So what you will do is you will use the points that are measured, and you will interpolate them in order to have a single value per pixel. So there are several ways to do interpolation, but in fact, we will use a convolution. Why? The first thing is that the visibility are noisy sample of a smooth function. And so making a convolution will smooth slightly your solution. And by doing the smoothing, you will increase your signal to noise ratio. So some smoothing is desirable to increase your signal to noise ratio. The second reason why is that nearby visibilities are not independent. So I've told you that each cross is a measurement in the Fourier plane of your source, but that's not exactly true. Okay, and the reason why it's not exactly true is the fact that the visibility function is the 2D Fourier transform of your intensity of the source times the primary beam function. Let's use again the Fourier transform property number 1, product here. This will give you the convolution of two functions, that is the Fourier transform of your source. That's what you are after. But in fact, it's convolved by the primary beam, the Fourier transform of the primary beam of your telescopes. So instead of having At each point, the Fourier transform of your source. At each point, you have some information. The convolution here, the size of the primary beam Fourier transform is this one, is the circle you see here. So at each point here, you have a convolution, so some information about the Fourier transform of your source inside the support given by each circle here. And so because of this, as long as your convolution kernel that you will use to interpolate the full width as maximum of this convolution kernel is smaller than the full width at maximum of the size of your Fourier transform of the primary beam, basically you will not change so much this equation, okay? You will not really lose information if this condition is met. So that's the second reason why we are doing interpolation by convolution. Fortunately, the measurement equation is kept through convolution. So before the gradient convolution, you have this measurement equation. And after the gradient convolution, you have this equation. This is exactly the same. But there is a condition, okay? Going from here to here, we have changed the definition of the dirty image and the dirty beam, okay? The dirty image now is the gridded dirty image divided by the Fourier transform of the kernel you've been used to interpolate. And the dirty beam is the gridded dirty beam divided by the Fourier transform of the kernel of your gridded function. Okay? The demonstration is here, okay, if you want to have a look at it. But I'm not demonstrating that if you're using those formula and the properties of the Fourier transform, you see that you will keep the form of your measurement equation. This is important because it means that all the mathematical algorithms that we use to deconvolve can be used on the gridded data, okay? And it was not obvious, okay? On the other hand, the mathematical form of the equation is exactly the same. It's a convolution equation, exactly the same as before grading. But we have introduced some grading, so we should not fool ourselves, okay? We have done something from going here to here by changing the definitions. And so there are artifacts due to grading that will enter into play. And that's what we will see in the next few slides. Okay, when we're sampling, let's show the effect of sampling a function. So here we have on the left column the UV plane at one dimension, on the middle column the image plane at one dimension, and on the right column what is the labels of each lines. Okay, so let's take in the UV plane a function f that is smooth. Okay, this is the Fourier transform of your intensity. And in the image plane, you're doing the Fourier transform of it, and this gives you the intensity distribution. Okay, so this is a strange source, but why not? And on purpose, it's going to 0 as at S here. So in fact, it's not exactly the source distribution, it's the product of the primary beam times the source distribution. And we will sample this regular function, the visibility function, regularly. So in order to do this, we will multiply this continuous function by a comb, a collection of Dirac function, okay, in the UV plane. And this gives you one value. You're multiplying both functions, and this gives you one value at each position, at each tooth of the comb. So this is what happens when you're doing regular sampling in the UV plane. Now let's look at what happens in the image plane. So the first thing is that you will make a convolution in the UV plane. No, sorry, a multiplication in the UV plane. So this means that in the image plane, you will do a convolution. Okay? You will convolve the Fourier transform of f, big capital F, by the Fourier transform of the comb, that is this function. So we are working the mathematics, and the Fourier transform of the comb is another comb. And the important property of this other comb is that the distance between two teeth of this comb is inversely proportional to the distance in the UV plane. Okay? So, making the convolution of those two functions will deliver this. Why? It's because a comb is a collection of Dirac functions. And when you're convolving a function with a Dirac, what you do is that you replicate your function at each Dirac. So here, for this Dirac, you're making a replication of your function here. For the second Dirac, you're making a replication here at this position. Third Dirac, you're making a replication here. Fourth Dirac, you're making a replication here. Okay? This is the convolution of one source by a comb. And what you do, in fact, you're doing the sum of the Dirac, and so you're doing the sum of your replication. But, so you see, in this case, there is not so much problem because the replicants, because the function is going to 0, the replicants are not going into 1 into 0. This is the result for a fine enough sampling. And now let's put the distance, let's increase the distance between the teeth of your comb in the UV plane. This will, for one of the properties, if you're dilating into this direction the UV plane, you will contract the image plane. And by doing this, the replicants will go closer together. Okay, and there is one critical sampling, which is called the Nyquist criterion, for which the replicants going to 0, the first replicants will go to will encounter the first replicant exactly where it's going to 0. This is the Nyquist criterion. Okay. Now, if you're doing an even coarser sampling, your first replicant will encounter the first replicant. The second replicant will go into the first replicant. You're telling me, well, that's the details, why should we care? Second example. So we are making this relatively continuous functions, but he has a point source at, a point source. In the UV plane, it has a spike at this position, okay? And so this is, by doing the Fourier transform of the continuous functions, you end up with this function here in the image plane. Now you're sampling. By sampling, you're multiplying by the comb at those positions, and this gives you those functions. By doing this, you have the first replicant and the second replicant, and you sum both of them, and the sampling is too coarse here. You see it? Because the spike here has not been noticed by the sampling here. Sampling is too coarse to catch this spike, okay? So you won't catch this. So in fact, what happens is that your second replicant is entering into the first replicant, and you have to sum both of them, okay? Now, this is for an infinite image, but you won't do an infinite image in practice. You will do a finite image, okay? And the finite image, you will cut it here, okay? And you will put, outside this finite image, you have no information, it will be 0. So the final result you will get is, in the image plane, is this function, okay? And the size of your image is this one, and outside, you have nothing. So in fact, if you're thinking about it, regular sampling, undersampling is twice as bad as you would think. In general, when you think about undersampling, you're thinking that by making your image, cutting here, you will not get everything that is outside the image size. The field of view is limited on your image, and if you have intensities that are outside, you will not see it. But that's not what happens. Because you have been undersampling, the intensity that has been outside your image has been folded inside and have modified the edges of your image. Okay? So undersampling in the UV planes is folding the intensity outside your image into your image. Okay? So this is called aliasing. So this means that in order to avoid this, you would have done an image that is from this one to this one, you would have not had any aliasing. So basically, this means that you need to make, in order to avoid aliasing, you need to make an image that is large enough. But how large? Okay, so the question is how big your image should be. So this is the image plane and the UV plane, and remember that the largest scale in the image plane is the pixel size in the UV plane, and the pixel size in the image plane is the largest measured UV distance in the UV plane. Okay? So in the image plane, the natural size of your image, I've told you since the beginning that what you measure is not the intensity of the source, but the intensity of the source times the primary beam. What is the primary beam? The primary beam is a Gaussian that is going to 0. Okay? So here, this is the full width attack maximum of your Gaussian. So here it's pretty flat, and it's going to 0 at about this distance, about twice the full width attack maximum. So this means that outside this image, you're going to 0, and thus you're not measuring anything. So the natural resolution in the image plane is twice the full width at maximum of your primary beam. Now, what should be the pixel size? So the pixel size in the image plane, it should be related to the largest distance in the UV plane measured. So the largest distance, let's say that this is this baseline, okay? And so you should do twice, this is an increase criterion, you should do twice this largest distance, okay? And this largest distance will be the angular resolution that you have in your image. And so twice the distance here would be half the angular resolution in the image plane. So you should select at least half the synthesized beam in the image plane. In fact, we are doing more than this. We are going from between 1/3 and 1/5 of the synthesized beam in the image plane for the pixel size. Why is this? It's because the deconvolution is a nonlinear operation. And in particular, you will see in the next lectures that we will use a clean algorithm that will search for point sources and we localize them inside the pixel. But for each pixel, it will put it exactly at the center of your pixels. And in nature, there is no reasons why your point source should be exactly at the center of the pixels. So there is some uncertainty, and the smaller you're making your pixels, the better the positioning of your point source will be, and that's why we are doing better than increased sampling. Okay, I've just told you that in the for the image size, we should do twice the field width at maximum of the primary beam. But that's only an approximation. This assumes that the primary beam is actual Gaussian. So here it's an actual primary beam. So this is the attenuation of the intensity, the sensitivity of the primary beam as a function of the angle. So you see that in the direction that you're looking at, the attenuation is 1, and then it's in log space, the attenuation is going very far down very quickly. So an actual Gaussian would be this function, but in fact, you have side lobes. Okay? This is the polar coordinate. The sensitivity is maximum here, and then where you're going as the angle, you start to have side lobes. So the side lobes are attenuated, and there is nothing we can do. The telescope is not perfect. We have side lobes. Okay? So I've just told you that the full width at maximum is this distance at -3 dB. Okay? And I've told you that you want to make an image that is twice this distance. So typically an image that is this one. But in fact, sometimes it happens that you're out of luck, okay, and you have a very strong quasar, 5-Jansky quasar, that happens at the position of one of the side lobes. You would have a point source that is here. You're making an image that is smaller, that is typically this size. So your point source that is here does not disappear. It will be folded inside your image. So you say, well, not a problem. I have a 5-Jansky point source, but it's so much attenuated that having it here, it will look like noise. Well, not always. If you're searching for very faint sources, you're searching for milli-Jansky source. 5-Jansky attenuated will be of the same order of magnitude. Okay, so this means that if you're unlucky, okay, and you have one point source, one quasar, one bright quasar at one of the side lobes of your primary beam, all of a sudden, by doing twice the image size, the primary beam size for your image, you will have a source that appears. So it's bad because this source is not, you cannot do science on this one. It's a spurious source. Fortunately, there is a way to see whether this is a spurious source or not. You're making a first image that is here, and you end up with a source that is here, that is being folded from here. But if you're making a second image that is twice as large, then your point source will appear at its right position. So in case of doubt, if you see point sources that seem strange or something strange in your source, okay, you will double the size of your image, and by doing this, you will see if the source is moving. If the source is moving, it's a spurious source. If the source stays at its position, it's a true source. So you could tell me, well, I will be conservative and I always will make an image that is very large, okay? Except that if you're doing this, you will spend plenty of disk space and CPU computers, and this means that you won't save the planet. So my advice is use two times the primary beam size for your first image, and in case of doubt, double it, okay? And see whether something is moving in your image. You have two beams in an interferometer, the primary beam and the dirty beam, okay? We'll speak more about the dirty beam in a minute. Here, the side lobes, and both have side lobes. And the side lobes we're speaking here are the side lobes of the primary beam, okay? Whether you have a spurious source in your image, okay, you should know that this can happen, but you're really unfortunate when this is happening, okay? Maybe it happens once every 20 years at Bure, so. Okay, let's speak a bit about the impact of the grading on the noise. So it happens that the noise is adding in the UV planes. You have measurements that are visibilities that are noisy. And if you're working out the mathematics, this will make a noise level that is flat in the image plane. So here what I'm showing is the RMS of the noise as a function of the angle in the image plane. Okay? And the angle, the size, here one will be half the size of your image, and 2 will be the full size of your image. But the image is centered in 0, so your image is going from -1 to +1. Okay? So your noise, the RMS of your noise is flat and constant in the image plane, and it has an infinite support. Okay? But now you will make an image. You will make several, by grading, you will make several operations. The first one is that you will convolve in the UV plane the visibility by the grading kernel. The convolution in the UV plane is a multiplication in the image plane. A multiplication by what? You're taking your grading kernel in the image plane, J, and you're doing the 2D Fourier transform. You get up with these functions. And your noise before grading is this one in blue. After grading, your noise will just be the multiplication by the grading, the Fourier transform of the grading function in the image plane. So this will be the red curve here. Okay? So you're starting from a noise that is flat, and by grading, the first operation of grading, you end up with a noise RMS that is going down to 0. But in fact, that's not exactly what is done by grading, because I told you that in grading, you have to make, not only you have to make the convolution, but you have in the image plane by dividing by the Fourier transform of the grading kernel. Okay? So here it's a convolution. So after the convolution, your noise is going down. Then you're making a finite image size. This one is assuming that you didn't make a finite size of your image, but by making a finite image size, you're folding everything that is outside the field of view of your image inside the field of view. So your noise is going from the blue curve, that was the red curve before, so this is the second point. This is the aliasing. You're going from the blue curve to the red curve because you have a finite image that you're taking. And then you're finishing your grading by dividing by the 2D Fourier transform of the grading kernel. So you're starting from the blue curve here. Your grading kernel has this form. You will divide it. It's going to zero. At the edge of your image. So inside you have some variation, but not so much. And all of a sudden you're going very close to 0, so it's diverging. Okay. So after grading, your noise is almost flat, almost uniform in the inner part of your image, but at the edges of your image, it will increase quite a lot. Okay? And what you get after deconvolution for a single pointing, a single field, what you will get is not the intensity of your source, but the intensity of your source times the primary beam. But what you're interested in is the intensity of your source. So basically, what you will, if your source is large enough, what you will do is you will divide by the primary beam. And this is the last step here. So the primary beam to first order is a Gaussian going to 0. Okay. And you're going from the blue curve to the red curve here by dividing by something that is going to 0. You are increasing even more the noise at the edges. You're increasing the noise so much, in fact, that in general, when we are doing the primary beam corrections, we're cutting out the field of view. We will see this more. Okay, so when we are grading, the next question you have to ask yourself is which kind of grading function you should use. So I've just told you that you need a function, you need a grading function that is going down very fast in the image plane to try to diminish the aliasing of this into the image you're producing. So it must go it must follow very quickly in the image plane, but it must also fall off very quickly in the UV plane. Why is this? Is because in the UV plane, the grading function is your kernel, and the biggest your kernel will be, the more smoothing you will do in the UV plane. So you will lose some information. So I've told you that it should be much smaller than the size of the primary beam, of the Fourier transform of the primary beam. So it should fall off also very quickly in the UV plane. But this seems contradictory because I've told you that a function that is small in the image plane will be large in the UV plane. So how can it be? Well, in fact, fortunately, it defines falling off very quickly in the image plane and falling off very quickly in the UV plane define a specific class of mathematical functions that are called spheroidal functions. That's a detail for you, but just know that in the Gildas implementation, spheroidal function as a default grading function. You can use other ones, but we discourage this because those ones are the ones that meet the best the requirements I've just put here. So spheroidals need to be tabulated, but that's a detail also to have fast computation. What about the quality of your dirty beam? So the dirty beam, the point spread function of your interferometer, the dirty beam is the inverse to the Fourier transform of the sampling function. So when I've been given the idea, the reasons why we should deconvolve, you immediately see that by convolving your source model by the dirty beam, the quality of your dirty beams will impose the quality of your dirty image. Okay? So that's why the quality of the dirty beam is important. And all the more than deconvolution is a delicate stage. And one of the most important information of this lecture is the following one. The closer to a Gaussian beam, dirty beam, the closer to a Gaussian the dirty beam will be, the easier the deconvolution. Okay? And in fact, if your dirty beam was exactly a Gaussian, you would not deconvolve at all. Okay? You would be done after making the image. Okay? So that's why getting a dirty beam as close as possible to a Gaussian is important. So what are the ways to improve the dirty beam shapes? First, you can add antennas. Okay, the largest number of antennas you will add, the better sampling you will have of your UV field, of your UV plane. Okay, and so it's useful to have a large number of antennas. So this is relatively costly. Okay, ALMA is 1.5 billions. NOEMA, one antenna of NOEMA fully equipped is 6 millions per antenna. The second thing, that once you have a limited number of antennas because you run out of money, the second thing you can do is change the layout of the antenna on the ground. Okay, choose different position of your antenna on the ground, and if the antenna are movable, move them. So once you have put some concrete on the land, the position of your station will not move, but then you can move the antenna from one station to another. It's not easy because the antenna needs to be the position of the antenna needs to be well defined. Okay, so practically it's difficult, and at BUR we are changing configuration a few times a year. Okay, so it's not easy. So fortunately, so let's assume that you get some times at NOEMA, some observation, and coming back, there are still something you can do when you're producing your image in order to change the dirty beam. And the way to do this is to weight the sampling function. Before going to the weighting of the sampling function, let's take an example. So in order to do some interferometry, you need at least 2 antennas. Here on the left, you have the position of the antenna, the sampling function for 2 antennas in the UV plane. And on the right, you have the associated dirty beam. Okay, the point spread function of this instrument. So the point spread function is the answer to point source. So you see that with the point source, you get up stripes. Okay, so it's difficult to know with 2 antennas, it's difficult to know that you have a point source. Now, a bit better. Sorry, let's go to 3 antennas. 3 antennas, you get a point source, but now you have to localize to know where it is localized. So it's difficult here also. Okay. 4 antennas, still difficult. 5 antennas, it's better. You have the impression that it's the point source is at the center, but you still see that you have side lobes of your dirty beam. 6 antennas, and then you end up with the plateau de Bure as of 2001. And then in 2011, we succeeded to have 15 more million euros to double the number of antennas. So 8 is giving you this, 10 is giving you this, and 12 antenna is giving you this point spread functions. It's not perfect. Okay, you see that probably your source is here, but you still have plenty of side lobes. Okay, fortunately, this is not what you get when you're having data. Okay, why? It's because here this is a single integration time. This is a snapshot. Okay, in fact, that's not what's happening. You have the Earth that is rotating. So during 8 hours, what count is, as Frederick said, what count is the projection of the position of the antenna on the sky. And because of this, each sampling point here will move along ellipses when the Earth is rotating. Okay? So let's do it. Let's assume that the source is rising at -5 hours before transit here, and here you are at -4.5. So you have at 3 measurements for each couple of antennas. So you see that all of the students, you have many more points observed, and all of students, your dirty beam is much better defined. And the sources continue to rise. And now you're at transit, well, a bit after transit. So you see that now you really see that your source is a point source. The associated dirty beam, the response to a point source is this one. But in fact, it's not completely perfect because you have part of the UV plane for which you have quite some negative side lobes close to the main lobe. And this is directly due to the fact that you have not sampled those parts of the UV plane. Okay? And that's why it's important to have long transit, long tracks, and here the source is going down, and 5 hours it disappears, but then you get quite a good associated dirty beam. Up to now, everything I've just shown you is for a compact configuration. You see that it's going, the largest baseline is going up to 300 meters. But in fact, you all know that in an interferometer, you can have different configuration of different extension on the ground. And so here I'm showing on the left, the sampling in the UV plane, and on the right, the associated dirty beam. on the top row for the compact configuration, and on the bottom row, the most extended configuration for NOEMA with baseline up to 1700 meters. Okay. So you see that you have, for a compact configuration, you have this response, and for an extended configuration, you have this response. So the main lobe is much smaller. Okay, so the response is much smaller. It's much better here. Okay, you get a much better angular resolution. So you're telling me, if I can have this response, low, very good angularization, why should we do any observation in the compact configuration? Why not always take the extended configuration? Well, the point is there is a price to pay to go to extended configuration. And the price to pay is the fact that you have a limited number of antennas. So the limited number of antennas means that you have a limited number, limited surface collecting area to get photons. Okay? In the compact configuration, your antenna will sample the inner part of the UV plane, and you will get plenty of sensitivity. You will maximize the sensitivity to your measurement in the UV plane because all the collecting area is measuring those. When you're going to extended configurations, you have the same number of antennas, same collecting area, but you have many more, much larger UV plane to samples. You need to sample many more points in your UV plane, okay? And thus the sensitivity is diluted on the extended dimension. So basically, if you have a single point source that is unresolved, you can go directly to the extended configuration. If you don't know, you should maximize your sensitivity and go first to the compact configuration, and then you see that it's not it's not resolved. Once you have done the first experiments, you're going to more extended configurations. This ensures that by doing to the compact configuration, you will have some detections. Okay? You should be a bit conservative. So I've told you that the sampling function is one where you have measured visibilities and zero elsewhere. But in fact, that's not exactly what we are doing. We are defining the sampling function as 1 divided by the variance of the noise for this visibility when you have visibilities that are measured and zero elsewhere. The advantage of this is that if you have visibilities that are noisy compared to visibilities that are high signal to noise ratio, you will take this into account in making your image. And you will make an image that has a natural weighting. This is called natural weighting. And this makes you an image that has the highest signal to noise ratio you can have. Okay? Natural weighting is what you should do to get your highest signal to noise ratio. So here I'm showing the sampling function for one experiment as a function of the UV distance. And you see that the sampling function, well, first it's oscillating, but more important, it's pretty large in the inner part of the UV plane and pretty small in the outer part of the UV plane. Okay? This is just due to the fact that this is exactly the same as here. This is due to the fact that when you have antennas on the ground, there are many more. What counts is the distance between two antennas. And the number of baselines that have small distance is much larger than the number of baselines that have large distance. Okay? There is nothing you can do against this. Any interferometer will do this. Okay? Any interferometer, the details will not be the same, but any interferometer will better sample the inner part of your UV plane than the outer part. Okay, what you can do, there are two possibilities to wait, because I've just changed the sampling function. Before I was telling you that it's 1, and now I'm telling you that it's 1 divided by the variance of the noise. So this is a mathematical transform. So this one ensures that you have the highest signal to noise ratio in your image. But why not continuing, and instead of taking your sampling function defined like this, let's add another function and multiply your sampling function by a weight. Okay, why not? It's another mathematical trick. And there are two possibilities. Either robust weighting will enhance the large baseline contributions compared to the smallest one, and tapering will do the same. It will enhance the small baseline contributions compared to the largest one. So robust weighting. So in each pixel of your image, okay, let's take this pixel, you have plenty of measurements. So what you will do is you will sum the sampling function for all of this, which is the sampling function is the weight. Okay, so you will get a weight per pixel. And what you will say is that if this weight, you will compute a W function that if the natural weighting is larger than a given threshold, then you will give this result. What it means is that in the inner part of your UV plane, you have a very good sampling, so you have plenty of weight. That's just what I've told you before. And you will decrease the weight of the inner part, okay? By doing this, you will saturate. By doing this, you will saturate your weight. On the outer part, you have a small, you have only, for instance, for this pixel, you have only one visibility. So because of this, the natural weight will be small, probably smaller than the threshold, and you will keep it. Why you will keep it? Because you don't want to increase you don't want to increase, to give more weight to noisy samples, okay? You're decreasing the weight where you have plenty of measurements, plenty of signal to noise ratio. You're saturating your signal to noise ratio. But in the outer part, you're keeping the natural signal to noise ratio of the UV plane. Okay. For the pixel size, we are typically taking 7.5 meters, which is half the diameter of the antennas, normal antennas. So this seems a bit strange, what I've told you, but let's take an example to give you an idea of what's going on. So the first column will be the dirty beam, the second column will be the dirty image, and the third column will be the clean image. And the top row will be natural weighting, and the bottom row will be robust weighting. Okay? So I will give the threshold that is 40 here, and then I will give the beam, the synthesized beam size, 1.4 times 0.89, 98, sorry, arc seconds. And then I'm going the noise value in Milizensky and in milli-K. And the same values for robust weighting. So you see that when I'm picking a weight, a threshold, when I'm picking a threshold that is large, it's so large that basically I'm taking the natural weighting. This is never happening. This is always happening because the threshold is large. Okay? So basically, with a large threshold, I get the same answer. Okay? Similar, not exactly, but similar beam and similar noise. But now let's reduce the threshold by a factor 4. And let's see what's going on. And by a factor 4, so 40 to 10, and then by another factor 4. Okay, let's look first at what happens to the clean image here. So you see that when you're reducing the robust weighting by a factor 4, you're getting a better angular resolution. Your beam, your synthesized beam is decreasing. You see that you get more details on your image. Okay, now let's look at what happens to the dirty beam. In the inner part of the dirty beam, you have a better definition of the beam, of the dirty beam. Okay? So basically, when you're doing robust weighting with a low weight, you're improving the quality, the resolution of your image. Okay? And you're improving the inner part of your dirty beam. So why should we not always use this? Well, we should not always use this because there is a price to pay. Okay, it's never free. Okay, and the price goes into the noise. So let's just look at the noise level. So with a large threshold, you get the same noise level as the vertical weighting, but with low threshold, you're increasing quite a lot your noise value. Okay, so you're doing not a robust weighting only when you get enough signal to noise ratio. If you're making a detection experiment, you're never using robust weighting. You want to have if in a detection experiment, you want to have the highest signal to noise ratio you can. In an imaging experiment, then you can do robust weighting if you get enough signal to noise ratio. So robust weighting increases the resolution, it lowers the side lobes, and it degrades the point source and brightness sensitivity. How to choose? That's your question. How to choose? What is the unit of your robust weighting? It's a complex unit. So instead of giving you the units, we just have a command in mapping that allow you to give the major, minor, and the noise level as a function of the robust weighting weight. Okay. So without weight, you get up, give the natural weighting, and with natural weight, and decreasing the weight, you will increase the angular resolution and increase the noise. So what you're doing is that you're choosing the robust weight that gives you a diminution of your signal to noise ratio by 10%, for instance, and a significant increase of your angular resolution. The second possibility is to taper your visibilities, the weighting of your visibilities. So tapering is that you will use as W function a Gaussian as a function of the distance, and T being the tapering distance. Okay. So basically, you're multiplying your weight by a Gaussian in the UV plane. This will translate into the image plane by a convolution. A Gaussian in the UV plane is a Gaussian in the image plane. So basically, what you do by doing this, you're convolving your image by a Gaussian. You're smoothing your image plane by a Gaussian. Okay? Again, same thing, natural weighting on the bottom row and tapering on the bottom row. I starting by choosing a taper distance that is so large that basically your Gaussian in the UV plane is constant. Okay, so basically the here it's in meter. The distance is so large that you won't do any difference with natural weighting. Okay, same solution in both cases. Now you're decreasing your taper distance by a factor 2 and by a factor 4. Okay? So by a factor 2, let's look first at the clean image. You see that you degrade your resolution. This is just what I've told you. You're smoothing with the Gaussian. So who is in right mind would ever do this? You have very good angular resolution. Why would you degrade this? Well, there is one reason. This is the fact that there is a gain by doing this, and the gain is in the noise level, but not both noise level in the. So let's first look at the point source sensitivity. The point source sensitivity will degrade by doing tapering. Okay, but the extended source sensitivity will improve. 10 milli-K, 9 milli-K, 4 milli-K. Why is this? This is clear, because when you all know that when you're smoothing an image, you will get higher signal-to-noise ratio for structures that are medium scale. Okay, you will increase the sensitivity to medium scale structures. Okay, and that's what happens here. So basically, you're doing this when you want to increase the signal-to-noise ratio to medium scale. For instance, in galaxies, it's a collection of point source, but sometimes you want to better see the spiral arms that are medium scales, and then you're tapering your stuff and you're making two images, one at high angular resolution and one at medium angular resolutions, and you will not see exactly the same, you will not do exactly the same science on both. So tapering, decrease the resolution, decrease the point source sensitivity, increase the brightness sensitivity to medium-sized structure. Another reason why you could do tapering is that sometimes your beam is elongated, your synthesized beam, the resolution you have is elongated, and by doing a tapering in the right directions, you can round your beam. But that's not the easiest way to do. It can be done, but it's not the easiest way to do. In a nutshell, you throw, by doing tapering, you throw away costly information, because in the UV plane, you're tapering, you're multiplying by something that is going to zero at the large UV distance. So basically, you have been asking to the program committee to make an image at high angular resolution, and then you say, well, no problems. I discard the large angular resolution. I'm using only the compact one. You've been throwing a large quantity of information. I remind you that 1 hour of observation at Bure is about 6,000 euros. Okay, so if you're stating I have two configurations, and in fact I want to keep only the compact configuration, you've been throwing quite a lot of money. So, in order to increase sensitivity to extended sources, don't use tapering. Try to use compact arrays. Okay? Sometimes you don't have the choice. You made a mistake, or you didn't know what was the structure of your source. Okay. But when you always start with compact configuration, if you don't know the structure of your source, this will make lots of economy.